students. Hello students, welcome to class 21. Okay, so today we'll go for the next concept of the water gas shift. Okay, so why this is so much important, and we know that this is nothing but syngas. Okay, so it is a combination of carbon monoxide and hydrogen, and we know that this is very much important, hydrogen, because petrol, coal is exhausting, and in the future we need some fuel, and the hydrogen is best replaceable for such fuels, okay, which is going to be exhaust in future years if we are using much of these fossil fuels. Okay, and how this hydrogen, which is alternate fuel for the fossil fuels, is got from the methane. Okay, so that is what we learned in the previous video, that is by controlled combustion of petroleum and coal gasification. So in that way we have seen that this syngas is obtained, and how this syngas is used in the Fischer-Tropsch synthesis of the hydrocarbon. Okay, so this also in the last video we have learned. Okay, and even the significance of this and the equilibrium, that is a shift equilibrium, water gas shift equilibrium. So what is that? We have given like H2O plus CO. Okay, so you can see that copper or iron, okay, as a catalyst is used, and the temperature is greater than 200 degrees centigrade, and you get water and CO2 with delta H minus 42 kilojoules per mole. Okay, so this is what they shift here, where we can see that carbon monoxide is oxidized to carbon dioxide, and we can see that hydrogen is so carbon monoxide is uh, oxidized here, and water, in water from the steam we are converting the hydrogen here. So this is what the concept of the equilibrium is we are going to uh, learn here. Okay, now if you go for this homogeneous catalyst, okay, what we had discussed in this year, so we are using some high temperature and catalyst, which are very costliest, and we are doing this, and in turn we are getting this syngas. Okay, this is equilibrium. Okay, so where we are removing this CO and we are generating this H2 in a more concentrated way. If you go for this homogeneous catalysis, so we know that metal, when is treated with carbon monoxide, okay, so this way, so it will coordinate it will coordinate to form this way. Okay, so like this. So this is what happens here, and finally we can see that the nucleophile I can write in this way, M C double bond O plus, and here you can see the nucleophile is going to be attached here like this. Okay, so this is concept is used in the what you say, in the homogeneous catalysis in a very mild condition. Okay, in a very mild condition. So this is the importance of the homogeneous catalysis of producing hydrogen, and carbon dioxide is produced, okay, and carbon monoxide. So Heber base reactions is given by Heber base reaction, so where this is used as monohydride FeCO4 minus anion. So this is what we are using as a homogeneous catalyst here. Now what will happen, now this will take the water, and OH minus is liberated here, and you can see you are going to get this compound intermediate CO4 like this. Okay, and from this you can see hydrogen is liberated out here. Okay, and we are going to get FeCO4 intermediate. Now when this is interacted with carbon monoxide, so we are going to get FeCO5. Okay, and from here you can see very important step here. So whatever the nucleophile here generated is interacted with here to get this compound Fe4 Fe C double bond O OH. Okay, and finally from here we get this compound by liberation of carbon dioxide here. So like this we can see the cycle of this water gas shift can be in a homogeneous and mild condition. We can obtain the fuel, that is your hydrogen, and the carbon dioxide is liberated here. So this is called the water gas shift equilibrium here. So with the help of this monohydride carbonyl complex of iron as a catalyst here, homogeneous, so you can see here, so when the water is treated, the liberated, what will happen, OH minus, because this will happen H plus plus OH minus here, and this H plus is added here, and you are going to get this intermediate here, and now this hydrogen is been liberated here, out here, H2, and that is what we require. Is it right? And this complex is here, FeCO4. Now one more carbonyl CO is added into this to form FeCO5, and finally you can see the OH group which was liberated in the first step is going to attack here, and you are going to get this intermediate as I have shown here, MC double bond O nucleophile here. So similarly iron C double bond OH, this nucleophile is added here, and from this you can see this this CO2 is liberated out, and we are going to get this hydrogen here, and we are going to get the starting material like this, and the cycle goes on what you say, repeatedly, so like this. Okay, so this is how the water gas shift equilibrium can be shown by the Hebers based reaction here. So very important. So, and here I think this is more than sufficient for the concept of the water gas shift here, because this is very much important for the, what you say, examination point of view, 2 marks or 3 marks they may ask. So this cycle plus some of the concept and Fischer-Tropsch this you can see. Okay, and what happens here, from water we are going to get the hydrogen, and CO is going to be converted to CO2. So this is what small difference you are going, a small this we are to point out here in this concept here. So here we will see if any problems on water gas shift if I get, so I will inculcate into this, I will put into this video, okay, or the coming future videos. Okay, now we'll go for the next concept of this, that is your hydrogenation. Hydrogenation. So this is the next concept of the catalysis, where we are using Wilkinson catalyst. Okay, we are using the Wilkinson catalyst. What is this hydrogenation? Hydrogenation is nothing but your addition of H2 into the alkenes. You take any of the alkenes here. So if you add this, like if I take this alkene here, okay, and if I add this hydrogen, so what I'm going to get, so I'm going to get this hydrogen is going to be added here in this way, and like this is already. So this is how alkane is been obtained here from alkene. Okay, and from alkene you are going to get alkane here, from the unsaturated to saturated, and this type of concept we call it as the the hydrogenation. And if you see that in the terms of catalyst, and you try to do this, it's highly costliest, and even temperature pressure is required for the hydrogenation. So very hazardous condition, we have to go for this if we try for the laboratory preparation. But if you go for again the homogeneous catalysis and heterogeneous organometallic catalysis, it can be very easy for hydrogenation of most of the alkenes, like a Wilkinson catalyst we are using, which is a homogeneous catalyst and very useful for hydrogenation at a normal mild condition. Is it right? So what is this homogeneous Wilkinson catalyst? That is nothing but rhodium chloride catalyst, PPH3 twice. This is your Wilkinson catalyst. Okay, so di triphenyl phosphine chloro rhodium 1 catalyst. This is your Wilkinson catalyst. Okay, so next we'll go for the cycle to understand the hydrogenation process. Okay, so I can give that the structure of the Wilkinson catalyst in this way. Okay, so this is PPH3, PH3, then PPH3. Okay, so this is the structure. So what I have given PPH3 in this one, PPH, yeah, here you make it 3 RHCl PPH3 thrice 3 plus 1 4, correct. So this is a structure here of the Wilkinson catalyst, where this is in +1 state, and if you see, this is a D8 configuration having a square planar structure. Okay, square planar structure, D8 configuration, where this the components are tetrahedrally coordinated, tetrahedrally coordinated, okay, ligands, we can see. And if you see the number of electrons here, so rhodium is 9 valence electron plus you can see 1 chlorine, and 1 2 3 2 3 4 5 6, so it becomes 16 electron species. Okay, so this complex is 16 electron species. Okay, so this is what about the about this rhodium complex. Okay, so this thing you have to keep in the mind. And square planar means hybridization, it is showing DsP2 type of hybridization. Okay, so this is what about this Wilkinson catalyst. Now what happens now when we add like this, we can show when we add the hydrogen here, so what is going to happen, oxidative addition is going to happen, and you are going to get the hydrogen attached like this in a form, this form, and the whole ligand and other things will be added in this way. Okay, like this. Okay, so other three ligands and this, and you can see the hydrogen is added, and again there is a shuffling from coordination +1 to +3. Okay, and even coordination number from 4 to 6. So like this, we call it as oxidative addition here. Even electron count also increases from 16 to 18 electron species. So this is how oxidative addition takes place here, where both the hydrogen is been attached in this rhodium complex. Okay, now what will happen, so here now next is one of this ligand, that is minus PPH3 is been minus PPH3 is been removed, which is trans to hydrogen. So if you see, this is removed here, which is trans to hydrogen, so this is removed, and you are going to get this compound. I will write here hydrogen, and here ligand, and here hydrogen, like this. Okay, so one type of TBP, that is your trigonal bipyramid structure, you are going to see here. Okay, and here you can see Cl is there. Okay, so like this, so the trigonal bipyramid structure is obtained here. Okay, so this is the intermediate obtained when one of the PPH3 is removed here. Okay, so now what will happen, now here there is now addition of alkene, or there is now addition of alkene here. I will take it here, alkene, CH2CH2R. What will happen here now, so you are going to get this compound RH. Okay, uh, H, H, this is what here, L, take it as Cl, L, and here you can see that the alkene is attached like this. Okay, the alkene is going to be coordinated to the rhodium here like this. Okay, so next what will happen, you know that next from here, so there will be beta hydride migratory insertion will be there. So I will write here beta hydride migratory insertion. So what will happen here, that one of the hydrogen will migrate. Okay, so migrate into this alkene chain, and you are going to get this compound. I will write here like this. Okay, so there is a migratory insertion of this hydride to this alkene chain, and you are going to see that you are going to get RH, H, El will be like that only, and this L is here as usual Cl, and here you can get CH2 CH2R like this. Okay, so this I'm going to get here. Again there will be oxidation state of rhodium plus 3, and you can see here hydride is beta hydride elimination. It is being added here, okay, like this CH2 CH2 CH2R. Okay, so one of the hydrogen is being included here, okay, and you can see that the double bond is being converted to single bond here. Now what will happen next step? So next step is your reductive elimination, okay, where you can see that this is been this is been out, that is CH2 CH3. Okay, so where you can see that the another hydrogen whatever is there is being introduced into this like this. Okay, so by reductive elimination, so now whatever is left is your RH, and this is your L, this is your L, and this is your Cl. Okay, so this is left. Now after this also is introduced into this here, and the whole bond gets eliminated. So what will happen? So this is bond is broken and this bond is eliminated here. So you are going to get here RCH2 CH3, which we require here from alkane. From alkene to alkane we got here, and left is what, one ligand is there, one ligand is there, and one Cl is there, and you are going to get this compound. Okay, again we are going to get this compound in ruthenium plus 1 state here. Okay, and this is a very reactive species now. So this species is very reactive. And now what happens here, if you add in this H2, it will go and form this here. So if you add H2, it is going to form this compound oxidative addition very fast to the level of 10 to the power of 7 like this compared to this. Okay, so starting what we are taking, then adding here. So instead of starting taking and adding here, this is the best that you remove first ligand first this one, and when this happens, so this has a capacity to add oxidative add this H2 to the order of 10 to the power of 7 faster than this. Okay, so anyway you can do that either this way or this you can do, no problem. Now finally you can see, then if you add now this ligand PPH3, now you are going to get this your original compound. Okay, so already PPH3 is there, one more you add, so you get PPH3 PPH3 and C, and this is generated. So this is how from the Wilkinson's catalyst we have produced from alkenes. You can see from alkenes we have done hydrogenation and we have obtained our product, that is your alkanes, this one. Okay, so this type of this this is how we can use we can see that the cycle is been the Wilkinson catalyst is very much important in hydrogenation process. And in each case you can see that how the coordination number oxidation state of rhodium from shuttles from +1 to +3 +1 +3 +1 and +3 like this. Even if you see the electron count 16 18 16 18, so like this it goes on transformation for all the for every complex whatever we are going to form, and even the geometry also. So from square planar to octahedral, from octahedral to TBP, again square planar, then finally trigonal planar this way. So geometry also is being changed here. And finally that is the fascinating nature of the catalyst, organometallic homogeneous catalyst. And finally in the under the mild condition you can see that the alkene is hydrogenated. Okay, so whatever the alkenes we had taken is hydrogenated, and alkanes is obtained here, so after the hydrogenation. So this is how about the cycle of the Wilkinson's catalysis. Now if you take the special characteristics of this special character of this Wilkinson catalyst, so we have to keep in the mind that this will attack only on less hindered side. Okay, so this will attack on less hindered side. So this is a one important concept you have to keep in the mind for Wilkinson catalyst. And always the rate of hydrogenation is fast for less substituted alkenes. Okay, the rate of is fast, that means mono alkenes is faster than di, then tri, then tetra like this. So this is the second concept you have to keep in the mind. It attracts for less hindered side. Then second is faster for the mono substituted, that means less substituted alkenes. Okay, and the third is terminal alkynes. If you are having the terminal alkyne and is faster, is greater than terminal alkenes, greater than terminal alkenes. Okay, alkynes is faster rate of hydrogenation than the terminal alkenes. Okay, if this condition is there, so this alkynes is very faster. Okay, and if even if there is a polar group, okay, if there is a polar group in the alkenes, so that will be faster. So hydrogenation is faster than the normal alkenes. This also you have to keep in the mind here. And even if there is conjugated dienes, okay, if there is a conjugated diene, so they are having the faster hydrogenation than the isolated alkenes. Okay, than the isolated alkenes. So this is how we can see some of the special characteristic of the hydrogenation. And if I go for order of the hydrogenations, we can take the order also. So always monosubstituted is having the faster. Then next one is this. Okay, next one is disubstituted, and from there you can see the cis form will be having. Then you can see the transform. Okay, then this is greater than the like this you can take, and finally this is greater than on the side you can see substituted like this. Okay, so this is the order of the hydrogenation. Okay, so always monosubstituted alkene simple is having the rate of hydrogenation faster than next is this compound cyclohexene, then this so compound followed by the cis form of the cis form of the dienes, then this is transform, double substituted, then followed by this again, and finally this is a rarest because it is highly substituted alkenes. That's why this is the least hydrogenated compared to the Wilkinson catalyst. Okay, so this is what we have to keep in the mind. Okay, now if you see some of the other catalyst, okay, some of the other catalyst which works very better than the Wilkinson catalyst is your this two catalyst they use, that is Crabtree. Okay, Crabtree catalyst. So this is what the one catalyst which is used, and even Schrock Osborne catalyst. Okay, something like that. COD is there here. I will do it here like this. Something. Just you can do it here. Rhodium catalyst. Sorry, rhodium catalyst. PPH3, PPH3. Okay, so this is Schrock Osborne catalyst, which is a rhodium catalyst. I will write here rhodium catalyst, and this is your chord cyclooctadiene. Is it right? 1 2 3 2 3 6 7 8. Okay, cyclooctadiene. So like this. Okay, so this is your I can write here rhodium cyclooctadiene, COD, PH3 triphenyl phosphine twice plus. So this is in the form of positive cation with PF6 minus as a counter ion. So this is your Schrock Osborne catalyst. Remember the Schrock Osborne catalyst. Okay, this one cyclooctadiene is there, and this is having the species cation species. Under this also helps in hydrogenation very faster than the your Wilkinson catalyst. So this is very much important. And one more this is there, that is your Crabtree. So again same thing here, so which is you can give in the same manner here. So as I had given now like this, and you can see here you can take here iridium, and here PCY3, and here pyridine is there like this. Okay, so this compound is your Crabtree. Okay, and this is what also, this also COD cyclooctadiene, and a 16 electron species. This also is a 16 electron species, and very important, I can say, very faster hydrogenation than the Wilkinson catalyst we are going to see in this case. Okay, so like this you can see, uh, if you see the order of the hydrogenation, so Crabtree is having the largest hydrogenation power, then this Schrock Osborne, then finally Wilkinson catalyst. This is how the hydrogenation power of this catalyst, homogeneous catalyst, is there. Okay, so in the hope you understood this. In the next video we will go for the application part of this, or some of the special characteristic of the Wilkinson catalyst and its properties. Thank you.